All right, so we are starting 7.2, so evaluating logs. So first off, it kind of fits in this one, but maybe not that much. First, I just kind of want to get into talking a bit about the Richter scale and earthquakes. It's a bit more to deal with. Sorry, one sec. From there. Okay, so sorry guys. Yeah, so the Richter scale really has to do with exponential functions, but like we saw last time, the exponential and logarithmic are really tied together. 30-3, we don't need to really think too much about the Richter scale and earthquakes in terms of logarithmic graphs. We can think about more just like looking at it with the exponential terms. But you know, it kind of fits in here anyway, especially if we were like in a 30-1 class or something, then we'd be solving for it using logs. But for us, what we mean by the Richter scale, I spelled Richter wrong apparently. So it's Richter scale. So the way this works, I don't know, you guys have probably seen this before, where someone will say, you know, it was 5 on the Richter scale, right? There was a 5, like a category 5 earthquake on the Richter scale, right? So what that means, right? So maybe you've got 5 and maybe you've got like 6 on a Richter scale, and then like an extremely bad earthquake would be like a 9 on the Richter scale. So what most people probably think, I think, when they're thinking of that, is that they're like, okay, well, if something's on 5 on the Richter scale, and then if something else was at 6 on the Richter scale, you'd be thinking, well, that's like a little bit worse, right? It's like, you know, that's a 5 and that's a 6, so you know, that's like one more worse than the first one. But it doesn't actually work that way with some scales, right? And this is called a logarithmic scale or like an exponential scale. And here's the way it works. So if something has a scale of 5 on the Richter scale, or a magnitude 5 on the Richter scale, that actually means this. It means that it's actually 10 to the power of 5, and that's how intense it is. So that's a 1 with 5 zeros behind it, right? So if something was 6 on the Richter scale, that's actually 10 to the power of 6. So now if we think about, like, you know, how much more intense is a category 6 on a Richter scale than a category 5? Well, what we can do is we can say how many times more powerful it is by going 10 to the power of 6 divided by 10 to the power of 5, right? Because that's like saying if I had something like 20 and something else that was 5, you'd say that this is 4 times more intense, right? 20 is 4 times more intense than 5. So the same type of thing here, just with bigger numbers. 10 to the power of 6 over 10 to the power of 5, that's actually going to be 10 times more intense, right? And as a little bit of review here, remember when you've got exponents, what our rule is? So if we had, you know, something was 10 to the power of 8 on the Richter scale, and they said, how many times more intense is that than something that is 10 to the power of 4? So remember, when you're dividing like things with the same base, the rule, the exponent rule here is that you subtract the exponents. So this would be 8 minus 4. That'd be the same thing as 10 to the power of 4. So if they were saying how many times is intense is something that is 8 on the Richter scale than something that is 4, it would actually be 10 to the power of 4 times as intense, which is 1,000 times as intense, right? Or sorry, 1,000, not, oh, actually is 10,000. 10,000 times as intense, right? So that's just generally the idea. So the other way that you might see this, maybe they get into decimals. So it might say, you know, something on the Richter scale measured 8.2. Okay, so then how many times more intense is that than something that measures 6.4? So you'd say 10 to the power of 8.2 over 10 to the power of 4. I forget what I said now, 4.6 we'll say. Okay, well, all you're going to do there, right, using our exponent laws, is that this would be the same thing as 10 to the power of, and then what do you do here? You subtract, right? So you'd say 10 to the power of 8.2 minus 4.6. Right? So in the end, that's the same thing as 10 to the power of 3.6. And then you could put this in your calculator and turn this into a number, but that's not going to be like 1,000 or 100 or base 10 type of a thing. That'll be some other number, right? But in general, that's the idea with Richter scales. So, all right, next part. So evaluating logarithms. So in the last video there, I kind of explained how exponents and logs are connected, and it says it all really right here. This is the difference, all right? So when you write the log of something, so when I write, I'm just going to write this again. So log base 2 of 16, this is a number. And what logs do, logs solve for exponents, okay? So what this is asking is, this is saying 2 to the power of what is equal to 16. So that's why my picture up here just has it written in a different way, right? So when something's written as like log base 2 of 16, that means the exact same thing as 2 to the power of something equals 16, okay? So a couple of things, like it says here, the base will always be the same. So if it has a log base 2, that's like the base part of the exponent. And then the 16 on the exponent, like on the equation here, is the same as like the 16 that's part of the log here. Okay? So I know this will be a little bit confusing, but here, let's do an example. So if I had something like this, if I said log base 3, and then it was 9, right? And that's equal to something, right? So that's actually going to be equal to some number. What I'm actually thinking when I'm looking at this log expression is, I'm saying 3 to the power of something is equal to 9. Okay, so it's solving for the exponent, right? That's what this something is. It's asking you, what would that exponent actually be? Okay, so in this case, that would be 2, right? Because 3 to the power of 2 is 9. If I had, if this was it, if I had log base 3 of 27, let's say, then that would be the same thing as 3 to the power of what is 27? 3 to the power of 3 is 27, right? So all of this is just the same thing as 3. Okay, so that's what we say when we say evaluating logarithms. That's what we're doing. We're actually putting a number to it. Now, that's true. Like that, we can do this in our head, ones that are like this, right? But the other thing you guys can do is you can put this in your calculator as well. So in your calculator, if you guys find your log, I don't have my calculator set up here like for my computer, but if you find, if you have a TI Inspire, then you would do this. You'd write log, and then right when you do it, it actually sets up like a little box there and another little box right there. So then it's pretty straightforward. You can actually just like put a 3 into there and put a 27 into there, and then it would give you an answer of 3. Okay, so that's pretty straightforward. If you've got like an older TI-83 and some TI-84s, I think, then they actually won't give you this little box. So you'll just type it in, and it'll just have a little box for you to fill in right there with a number. Remember the way that this is that when it's just log without any kind of base to it, it's assumed that you mean log base 10. Okay, so the way that you actually write this in would be, so if I wanted to write in, let's say that this one above where it was log 27 over, or sorry, log base 3 of 27, you would write it this way on a TI-83. It would have to go in as log 27 divided by log 3. Okay. So if you're having trouble with that one, we can work on that. But yeah, maybe come into my open hours, but it's just like log of the top one divided by log of the bottom one. That gives you the same answer there. Okay. Okay, so that's in general, that's the idea. So let's do some examples. So here, I'm actually gonna look at your guys' assessment and grab some examples that are similar to those ones. So if I was smart, I would have had it open. Oh. Okay, so let's say we had this. Let's say we had log base n to the, or of u is equal to r. And the question says, write this logarithm in exponential form, right? So we're gonna have to be able to go back and forth. We're gonna have to write logarithms in log form, and we're gonna have to write them in exponential form and go from one to the other, right? So if this is my question, if we're saying, okay, this is my logarithmic form and we wanna write it in exponential form, I always find a good place to start is with the base, right? So what's the base? Because I want this to be an exponent, like so something like this. So the base, like it says here, is always the same number. So base 2, base 2. So I know right off the bat, I've got base n, right? It's a letter, but that works. So it's going to be n to the power of something is equal to u. Well, remember that it's logs solve for exponents. This number here is the exponent. So that's going to be n to the power of r, and then that's equal to u. I find quite often, like in my mind, I kind of have this pattern where I'll go n to the power of r gives you u. It's kind of like that pattern where it goes to the right and then over. So n to the power of r gives u. Okay. And if you're going back the other way, let's just go back now. So this is in exponential form. We can go back again by saying you do it this way and say log, and then base n. That's kind of a good place to start, right? Where it's always the base will be the same for both of them. And then it's going to be like this number here that's in front of the log is what it's equal to, right? So that's going to be u is equal to, and then this is the exponent. Okay, so we need to get good at just going back and forth. It doesn't matter if we're not using numbers, right? It's the same process, even if we're using letters like this. Okay, so let's do another one here. So we'll say, what about, this one says, put it into logarithmic form. So if we started off with this and say 3 to the power of n is equal to a. And the question says, put this into logarithmic form. Okay, so I'm thinking base, right? Like what's my base here? Well, my base is 3. So I can just start writing that out. Log base 3. And then remember that you might even want to do this one first, like the exponent is this part. And then it's and then it'd be that one, right? So it's, once you get to this, you can go back the other way and say, okay, 3 to the power of n is equal to a, right? 3 to the power of n is equal to a. So yeah, so make sure you guys practice going back and forth on those ones, because that's the idea there. Okay, let's do one like this, and then I think we'll be done, because this is pretty much it for this lesson. We'll get more in depth into the next one, but let's say we had this. What if we had 2 to the power of x plus 3 is equal to 4? And we want to write this, and it'll ask us maybe to write this in exponential form. All right, so again, base, right? I'm thinking, okay, what's my base here? So it's going to be log base 2, and then of 4, right? So of 4 is equal to x plus 3, right? So that's the idea. So now it's actually all down on the same level there. Now, like maybe the question didn't ask us to do this. Like I don't think I didn't in your homework questions that you're going to do. But what the idea here is now is that I could solve for x, right? This is why logs are important, is because now that I really the problem up here, if someone asks you to solve for x, you guys can do that by well, we did a bit of that. You can make like common bases if you can from our exponents unit, or you could graph it. But sometimes, if you want to do it algebraically, we got to get this exponent down into the main level. And this is how we can do it, right? Because now looking at this, I've got, I can actually solve for x, right? Let's actually solve for x. I can actually do that now. So what we can do is get x on its own. So I'm going to bring this 3 over to the other side. So I'm going to subtract 3. So really what we got going on over here, this is log base 2 of 4 minus 3 is equal to x. Now, you might want to grab your calculator right now, right? Because you're like, okay, that seems really hard to do. But it's not that hard to do, because looking at this, remember what logs do. Logs solve for exponents. This is saying 2 to the power of something is 4. Well, I'm thinking you guys can do this one, right? 2 to the power of 2 is 4. So all of this is just 2. So this is really 2 minus 3 is equal to x. And then you could say 2 minus 3 is negative 1. So x in this case would be equal to negative 1. So there, we solved this one algebraically, right? We didn't even have to graph it to figure that one out. Okay. So just one sec. Oh, I better do one like this too. So there's one other example here. Let's say we had one like this, that we had log base 4 of 1 over 64. And it said, what is that equal to? So again, you could punch that in your calculator and it would give you the right answer to this, right? But we don't really need to, because what I would do here is I'd say, okay, well, 4 to the power of something is equal to 1 over 64. And I know the fraction kind of throws everybody off, but if you look at the 64, I could ask myself this too, right? 4 to the power of what is 64? So 4 to the power of 3 is 64, right? And what about 4 to the power of negative 3? What does that give you? Do you remember how like the negative on the exponent actually flips it upside down? So 4 to the power of negative 3 actually is 1 over 64. So this is really just negative 3. And there you go, right? 4 to the power of negative 3 gives you 1 over 64. So, yeah. Oh, and then last, I should go over this one too. I keep telling you we're done, but I just want to go over Euler's number and natural logs as well, because we can do the same thing here, right? So let's say we had a question like this, where it wanted this in exponential form. So you had natural log of d is equal to 7. Okay, so what does that even mean? So remember what the natural log of actually is, right, from our last lesson there? Natural log is this. It'd be the same thing as writing log base e of d, right? Remember, e is Euler's number. It's like, so Euler's number was like that 2.7 yada 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 number. It's just a really common number in math, right? So it comes up enough where it has its own symbol for it. So if I've got that is equal to 7, well, now this is just like before, right? I'm going to say, if I want this in exponential form, I can say e to the power of 7 is d. E to the power of 7 is equal to d. So that would be the same thing. Okay, so whenever you see like a natural log, just think about that as actually being a log with a base of e. Okay? And that is it. So I'll leave it at that, guys. It'll get a little bit more complicated as we go, but for now, that's everything we need.